The last class of functional groups that we're going to cover for now are the carboxylic acids, esters, amides, and acyl chlorides. So let's start with the carboxylic acids and map out its electron density. Of course, we have a potential nucleophilic oxygen, and we have pi electrons that could be nucleophilic. However, we have this delta plus electrophilic carbon. We also have a potential nucleophile at the oxygen because of the lone pairs. And then we have an acidic proton. And this is usually a pKa of less than 10. So this is a very acidic, as the name implies. The functional group is called the carboxylic acid. And so the proton there on that particular oxygen is acidic. And if you recall, the reason it's so acidic is because the conjugate base is resonance stabilized. In terms of intermolecular forces, carboxylic acids exhibit dispersion. They have dipole-dipole interactions because of the polar C double bond O, and you also have a bond polarity on the other side between the carbon and the second oxygen. But then what carboxylic acids are very, very good at doing is hydrogen bonding, because you have an H bond donor and acceptor. And actually, carboxylic acids are very good hydrogen bonders. And when they're concentrated enough, they exist almost in these long extended states where you have a lot of extensive hydrogen bonding taking place. And so they have very high boiling and melting points compared to, say, an alcohol. Next, we're going to look at the esters. Left off a couple of lone pairs here. And the esters are have the general formula as shown here. I'm putting on here the notation that you might see shorthand for an ester if you don't have the skeletal structure like this drawn out. And an example of that is shown below. In terms of mapping the electron density, it's very similar to the carboxylic acid. You have nucleophilic oxygen, you have nucleophilic pi electrons, you have an electrophilic delta plus carbon, and you have a nucleophilic oxygen on this side. What's different is you don't have an acidic proton, so that's what makes an ester different than a carboxylic acid, is that now you have a carbon on the other side of that oxygen, so this is not an acidic species. As far as intermolecular forces go, of course we have dispersion, we have dipole-dipole, and this time we do not have hydrogen bonding because you have H bond acceptors but no H bond donors. So between two molecules of ester, you will not see hydrogen bonding taking place. However, if you were to put this in the presence of a donor, like water, then you could get hydrogen bonding between the ester and the water. Amides. Like the amines, there are different types of amides. When you have two hydrogens and one carbon on the nitrogen, we're going to call this a primary amide. That's kind of the most simple amide you can have. When you have one hydrogen and then two carbons, that's going to be secondary. And then when you have only carbons around the nitrogen, that's going to be tertiary. And kind of the generic way that you could see, depending on if the amide is primary, secondary, or tertiary, but you're going to see maybe for example, something like this. This would be a primary notation. And then of course we could write, say for a tertiary, you might see it, the shorthand written like that. So let's map out the electron density of an amide, and here I'm not really specifying if it's primary, secondary, or tertiary. In all of those cases, you would have a nucleophilic oxygen, you would have some nucleophilic pi electrons, you would have the electrophilic carbon, and you would have a nucleophilic oxygen. What is different between primary and secondary versus tertiary is that if you have a proton here, this is acidic. pKa's are usually, it can be less than 20. So compared to an amine, this is more acidic. And I'd like for you to think about why that is based on what you know about acidity. In terms of intermolecular forces, amides exhibit dispersion. They exhibit dipole-dipole interactions. And if it's primary or secondary, they also have the components for hydrogen bonding. You have the acceptor here, and you have a hydrogen on the nitrogen, so that can be a donor. So you can get between primary and secondary amides, you can see H bonding. Of course, the tertiaries would not have that hydrogen to donate. Lastly, in this video, we're going to consider what's called the acyl chloride, sometimes called an acid chloride. You can use those terms interchangeably. And if we take a look at the electron density here, once again, hopefully you see a pattern with all of these. There's nucleophilic oxygen, nucleophilic pi electrons, electrophilic carbon. And then you have potentially a nucleophile with the chlorine atom. No acidic protons. And then in terms of IFs, we have dispersion and we have dipole-dipole. You have an H bond acceptor, but no donor. So like we've seen over and over again, two molecules of acyl chloride are not going to hydrogen bond to one another, but if you were to put them in with water or another H bond donor, then you could see hydrogen bond interactions take place.